not obviously trigonometric integrals. So let's take a look at these two. I have the integral of square root of 1 minus x squared, or an integral of a square root of 1 plus x squared. Well, they don't have any trigonometric functions in them, so why would we be covering them in this particular section? Well, that's because let's just take a look at this first integral. How would we approach it in the first place? There's nothing I can substitute for, because what I would really like to substitute for is the inside of a square root. But if this is my u, then my du is going to be minus 2x dx. And I don't have this extra factor of x anywhere in this integral, which means that the substitution will not work. Well, what else is there to try? There is nothing that will help me break apart this integral at all, so my other attempts at simplifying are stopped before they can even begin. One thing to remember here, though, is that 1 minus something squared is an identity we've already seen earlier today. In fact, let's recall not one, but two basic trigonometric identities. They come from the same idea, but can be written differently. I have that sine squared x plus cosine squared x is equal to 1, which can then be solved for either sine squared or cosine squared. Let's say here I can solve for cosine squared, and I will get 1 minus sine squared x. And this is kind of like the form of what we have under the square root here. The square root will in fact make it even simpler, because if I square root both sides here, I notice that on the left-hand side, I can cancel out the square root and the square to produce cosine alone. So the even powers here really help us to simplify the square root. My second basic trigonometric identity can be derived from the first one by simply dividing everything by cosine squared x. What am I going to obtain? Sine squared x over cosine squared x is tangent squared x. Cosine squared over cosine squared is simply 1, and 1 over cosine squared is secant. So this is how we get to our second basic trigonometric identity, the fact that tangent squared x plus 1 is equal to secant squared x. I'm going to rewrite this in the most sort of useless form, but just to be consistent with the previous line, I'm simply going to swap left and right sides here. So secant squared x is equal to, well, let me swap the signs or the constants too, just to align everything to what I have above, 1 plus tangent squared x. And now let's see, this 1 plus something squared is in the same form as this, 1 plus tangent squared. And again, taking the square root is not even going to be detrimental here, because if we replace the right-hand side with the left-hand side here, the square root and the square simply gets cancelled, producing a reasonable expression of simply secant x. So then, let's think, for example, about taking this one integral, and how would that look if I am to replace 1 minus x squared with 1 minus sine squared. First of all, our very first consideration has to be the fact that I need to be mindful of the domain. What I have here currently is that the inside, what happens under the square root, has to be positive, because otherwise I simply cannot take the square root of that number. Am I guaranteed that by performing this substitution, what I get is going to be positive? Well, this is the one nice thing about trigonometric functions, is that they are bounded between -1 and 1. So the smallest sign can be is -1, and then all the way through 0 to the biggest it can be is +1. So this expression, no matter what the sign value is, will in fact always remain positive, which works out just perfectly fine for my domain. So if I can perform this substitution and replace the inside of my square root with this trigonometric expression, I will be safe in terms of where my function is defined. In this lecture, we will take this integral and go through to see exactly how this type of substitution will work. So let's start off, grab a blank piece of paper because this is going to be a lengthy process. And what we'd like to do is figure out how to evaluate the integral of square root of 1 minus x squared dx. So based on the previous discussions, what I would like to do is substitute x equals sine theta for some angle theta that I'm not going to specify, and then see how this works out through the actual simplifications. So within the normal substitution box, once I figure out what x is, I need to calculate dx, which in this case is going to be cosine theta d theta, and then I'm going to plug all of this information back into my integral. Notice that this time the substitution is a little bit different because I'm not taking an expression in the integral and calling it a new variable. Rather, I'm taking the x, the variable itself, and replacing it with a new expression that will allow me to simplify the square root that I currently cannot break down at all. So once we plug it in, let's see what simplifications will occur. So what are we going to have here is I'm going to have 1 minus x squared. Now x is sine theta, so I'm going to have sine squared theta, and then times dx, which is this expression here. So times cosine theta d theta. Now at this point, this is exactly where the basic trigonometric identity is going to show its usefulness, because I can replace this 1 minus sine squared theta with cosine squared theta. So recall that according to the basic trigonometric identity, I have this relationship between sine and cosine of any angle. So I'm going to utilize this to substitute in for 1 minus sine squared theta here. This expression under the square root is cosine squared theta. So what I end up with, of course, is, let me write the intermediate step as well, square root of cosine squared theta times cosine theta d theta. So what do I have? Well, now I can see exactly why this was a useful substitution, because I end up with a perfect square under the square root, which means that I can cancel it all out, and in my next step, I simply have cosine theta that results from this square root of cosine squared theta. And then I inherit the second cosine theta d theta. So my resulting integral is actually cosine squared theta d theta. Now this is one of the integrals that we discussed in previous lectures. This is now a trigonometric integral with the even power. So the way to attack it is to use half angle, or depends on how you call them, double angle identities. So I'm going to break this one down, and recall that the identity suggests that cosine squared theta is actually equal to 1 plus cosine 2 theta over 2 d theta. And now this integral I can break apart. First of all, I can take out 1/2. And what I'll have in the integral left over is going to be 1 plus cosine 2 theta d theta. And now I can integrate it in pieces, right? The integral of 1 d theta is just theta. So don't forget the 1/2 outside. So this is going to be theta. And then I'm going to have plus the integral of cosine 2 theta. Now the integral of cosine 2 theta, the antiderivative is sine 2 theta, and the chain rule, or the anti-chain rule really, will suggest that I have to divide by 2. All of this plus a constant. I can open up the brackets just so I get an expression that has no factors. So I'm going to have half theta plus sine of 2 theta over 4 plus c. Well, this is fantastic news because I have solved my integral. This expression no longer has an integral in it. And let's just review the process really quickly one more time. So I started with an integral that had a square root and an expression under it. As written, this square root cannot be simplified because I cannot break up the square root over the negative sign. So there's nothing I can do with this integral as is. I will therefore employ a trigonometric substitution that will allow me to use the basic trigonometric identity under the square root to be able to obtain a perfect square that will cancel out with the square root. This will produce then a trigonometric integral that I can solve using previous techniques, and I can fully integrate my expression. The problem is not complete though yet, and that is of course because this is not in terms of x. Remember that my original integral was in terms of x, and we always want to come back to the original variable, which this is not yet it. So now I have to figure out how to go from theta back to x. I'm going to utilize my substitution box here, and there's actually two slightly different ways to do it. We can do it algebraically, or we can draw ourselves a little triangle. Before we do that, let me actually simplify this expression a little bit more. I know I'm going to have to go back to x's, and I can see that here I have sine of 2 theta, so a trigonometric function of twice the angle theta, whereas x itself is just a trigonometric function in terms of theta. So in terms of making it just slightly easier, I can first of all rewrite this sine 2 theta using a trigonometric identity as 2 sine theta cosine theta. That's what sine 2 theta equals to, according to the double angle identities, over 4 plus c. Now I can see, of course, that I can cancel one of the 2's here. So let me go ahead and do that. So this will then be sine theta times cosine theta over 2. Right? So again, how do we get back to x's now? We're going to see two methods, algebraic and a geometric one. So first thing that we have to remember is the connection between x and theta. And this is given to us by the substitution box. We know that x is equal to sine theta, and we also know that we would like to express things like theta, sine theta, and cosine theta in terms of this x now. So let's write down what we have. X is equal to sine theta, which means, by the inverse trigonometric functions, that theta is equal to arcsine of x. Now, sometimes it's also written as sine inverse of x. I generally prefer the arcsine notation because it's very clear that it's an inverse function and not a reciprocal. This one is not the best of notations, so I will stick with arcsine. But if you're more comfortable writing sine inverse in this manner, by all means, go right ahead. So let's take a look at our final expression to see what we need. Well, now I have theta expressed in terms of x, so I have this portion of the answer covered. I have that sine theta itself is x, so that means that this part is covered, and all that remains is for me to be able to express cosine in terms of my existing x, which means in terms of sine. Now, going back through the basic trigonometric identity once again, I know that cosine theta is equal to square root of 1 minus sine squared theta, which means that this is equal to 1 minus x squared. Now I'm going to plug in all of this information into my final answer for the integral here to be able to rewrite the whole thing in terms of x. So what I have here is now that my original integral 1 minus x squared dx is equal to, let's read this off, a half of theta, and theta is arcsine of x, so I have a half of arcsine of x plus, then I have sine theta times cosine theta. So sine theta is just x, so first one is just x, and then cosine theta, which I derived to be square root of 1 minus x squared, all over 2 plus a constant. All over 2 plus a constant. And that is my final answer here. You can, as usual, check your final answer by taking the derivative of this and seeing if it's going to equal to the expression in the integral. It's surprising that an integral that only has square roots and a polynomial actually ends up having an inverse trigonometric function in it, but that's exactly why we use the trigonometric substitution, because these integrals are actually sort of hidden trigonometric integrals. Now, I promised you the second way to go back to x's. So the first way is algebraically, and the second way I'm going to call it geometrically. So this is using a picture. What we have to come up with here is, instead of basic trigonometric identity, I'm actually just going to use a little triangle. Now, the first line is going to remain the same, and that is because this is given to me by the substitution box, and there's simply nothing else I can use. This is the definition of what theta is. Theta is arcsine of x. But now geometrically, let's remember that sine is opposite over hypotenuse. And therefore cosine, which is what I need in my expression in the end, is adjacent over hypotenuse. If I'm talking about opposite and adjacent and hypotenuse, it makes sense to draw a little right angle triangle. There we go. Now, it doesn't actually matter how you label your angles as long as you're consistent. So let's say this is going to be my theta. And again, it doesn't matter which non-right angle you pick for theta. You can pick this one. You'll end up with the exact same mathematical expressions. So what I have here, what I am given, is that x is equal to sine theta. Remember that sine theta is opposite over hypotenuse, which means that now I have to label the three sides so that the sine of this angle ends up being equal to x. Now, opposite over hypotenuse, so this side divided by this side has to equal to x. Now, x itself is just one number, so it's probably easier to think of it as x over 1. And then you can easily see that you have to label opposite as x and hypotenuse as 1. Now, this is, of course, all up to scaling. So I could, for example, also write this as 2x over 2, and then label opposite side of theta as 2x and the hypotenuse as 2, and you'll end up with the same expression. I am simply choosing the simplest of the forms. Now, this is what sine of x is, and again, going back to our integral, our final expression, I have my theta, it's arcsine, I have my sine, which is just x, I need cosine. So now I have to think of what is cosine of theta in the triangle. In the triangle, it's adjacent over hypotenuse. Now that means that I'm going to have to figure out what are those corresponding sides. As far as theta is concerned, adjacent is this side, whose length I don't know yet, and hypotenuse is 1. So I can insert the piece of information that I have. Now, how do I figure out the length of this side? Well, it's a right angle triangle, so I can simply use Pythagoras. Recall that the sum of squares of the two sides is equal to the square of the hypotenuse, which means that this side is going to be square root of hypotenuse squared minus the other side squared. 1 squared minus x squared, or 1 minus x squared. Now here, dividing by 1 isn't really doing anything, so this is simply equal to 1 minus x squared. And so I end up, of course, with the same expression for cosine as I did using the basic trigonometric identity. And this is really just another way of thinking about the basic trigonometric identity. It's really Pythagoras' theorem in a slightly different written form. So in the end, my answer for the integral 1 minus x squared dx is, as before, 1/2 theta, which is 1/2 of arcsine x, plus sine theta, which is just x, times cosine theta, which is root of 1 minus x squared, divided by 2 plus a constant. So both times I end up with the exact same formula. So let me just take this, copy it over, and I can insert the exact same expression here because it ends up being exactly the same. This is the full example of applying trigonometric substitution to an integral. Let's go back through the steps. So first of all, we have to recognize that we cannot simplify the integral as is, and therefore we'll have to perform some kind of trigonometric substitution. We have to figure out exactly what it should be, and we're going to talk a little bit about this in just a little. And then, once you've plugged everything in, we have to use trigonometric identity in order to simplify the expression and specifically get rid of the square root so that I end up with a trigonometric integral I can in fact evaluate. Once we evaluate this, we have to be able to get back to the original variable x, and we can do it either algebraically by sort of reverse engineering through the substitution box and the trigonometric identity we used, or geometrically by drawing a picture and using the SOHCAHTOA type of logic. Trigonometric substitution examples are always long. The hardest step, however, is going to be choosing the correct substitution and then making sure you end up with the integral that you can evaluate. So let's talk more about how to pick what trigonometric function matches the corresponding integral. This table summarizes everything about which trigonometric substitution to use when. So let's take a look, first of all, at the identity column. This column lists the trigonometric identities that motivate the corresponding substitution. So in the example that we've just seen, we used this particular identity with the substitution x equals sine theta. What the more general expression suggests is if there is a constant here, let's call it a, I can still use this substitution, but I have to scale it according to the given constant. So this a is a constant, this x is your variable. Keep this in mind throughout. So if I have an expression inside my integral that includes a square root of some number minus my variable squared, then my corresponding substitution is going to be sine, probably scaled by some number, and the identity I'm going to utilize is the one between sine squared and cosine squared. If inside my integral I have an expression that involves a square root of some number plus the x squared, then the substitution is going to involve tangent, potentially scaled, and the identity I'm going to use is the tangent squared and secant squared one. On the other hand, if I have a square root of x squared minus a number, so notice the difference between these two here. In one, I'm subtracting x squared, and in the other one, I'm subtracting from x squared. In this case, I'm going to use the substitution that involves secant and the trigonometric identity that again involves secant and tangent. This takes just a little bit of practice to really get a handle on it. So what I strongly recommend is that you pause the video here and take a look at these integrals and come up with the correct substitution using this table. Don't solve an integral, that's a whole other process, and again, it's always going to be a lengthy one, but the first step is key, using the right substitution. Take a minute here, stare at each one of these integrals and the square root expressions that they involve, and try to find which substitution based on the previous table will work. Then come back and we will go through the answers. Okay, so I'm assuming you were good students and actually got your pencils out and tried out these substitutions. So this first one here, I have a number plus x squared. So this immediately suggests that I'm in this situation here. And the one thing to watch out for is the substitutions are always given with a constant a, where the number that I have under the square root is actually a squared. So in my first case here, and for the first few integrals, it might actually help to, first of all, write out that this number, 9, is actually 3 squared plus x squared. And then it's easier to match to see that this is going to be my a squared, this is going to be my x squared, and therefore the substitution suggested by the table is going to be 3 tangent of theta. Now this simply asks to use the substitution or to come up with the correct substitution and leave it as is. But for this particular question, let's just take it one step forward just to see why this actually works out. So what I'm going to have to do next is differentiate this x in order to come up with the next step. So here I have to take a derivative of 3 tangent theta, and the derivative here will be 3 secant squared theta. So now let's plug all of this back into my integral. So what am I going to have? I'm going to have integral of 3 squared. So let's leave it like that. 3 squared plus x squared, which is going to be 3 squared times tangent squared theta. 3 squared, tan squared theta, times dx, which is 3 secant squared theta. D theta. Whoops, I forgot my d theta yesterday. Shame on me here. There we go. You can't have an integral without the differential. Okay, so what I can do here now is I can see that I can factor out 9 from both of these guys. And so what I end up with is square root of 9, 1 plus tangent squared theta times 3 secant squared theta d theta. Excellent. Let's see what we can do now. Well, first of all, I can, of course, now split this square root over the times. Or I can actually just, first of all, transform this 1 plus tan squared theta into something else using the corresponding trigonometric identity. This is once again where this table is going to be useful. This is the line that I used. This was the expression in my integral. This was the substitution I performed. This is the identity that's going to prove to be useful. And this says that 1 plus tan squared theta is equal to secant squared theta. 1 plus tan squared theta is exactly what I have. So this right here is going to equal to secant squared theta. Then I'm going to skip a step here. Feel free to pause the video and make sure you actually understand. But my next step is going to be 3, because that's the square root of 9, times the square root of secant squared, so secant, and then I inherit this other part, 3 secant squared theta d theta. That's it. I can simplify this integral further and actually evaluate it. I am going to not go through these steps because up until now, this is more or less the hardest and the most essential key to trigonometric substitution. Choosing the right substitution with the correct constant ensured that this constant can be factored out because then it was common to both terms under the square root. This allowed us to implore the trigonometric identity that corresponded to the trig substitution, and in the next step, get rid of the square root entirely. If you come up with an integral that no longer has square roots, that means that the trigonometric substitution actually worked. So for the rest of them, what do we have here? I'm not going to go through the rest of these integrals in detail. I'm simply going to list the corresponding trigonometric substitution that should work out. And I encourage you to actually go through and substitute it in, use the trigonometric identity so that you get some practice with it, and ensure that in the next step you get an integral without any square roots. So what do we have here? I have 9 minus x squared, so a number minus x squared. A number minus x squared is the first line in the table, which suggests the substitution of this constant times sine theta. So in this case, this is going to be 3 sine theta. Let me maybe make a separation here. There we go. Okay, and again, I'm not actually going to go through with these. I'm just going to list the substitutions. What about this time? Well, here there are two ways of thinking about this. I can either consider this to be 1 minus 3x all squared, square root, or I can also think of this as first factoring out the 9 and ending up with 1/9 minus x squared. Either way you choose to look at it, what we need is to figure out what to substitute for this x in terms of trig functions so that I can create a number in front of it that will work with the number provided to make the trigonometric substitution actually work out. I prefer to think of it in terms of this way, and this suggests that whatever is under the square root has to be replaced by the corresponding trig function. So here I have a number minus something squared. So going back to this, a number minus something squared is this expression, which means that my trig substitution has to involve sine, which means that if I simply replace this expression with sine, this will work out. But now my expression actually contains 3 as the number, so overall my substitution can be 3x is equal to sine theta. If you prefer to think of it this way, and first of all get rid of the number in front of x so that you are more in line with the format of the substitution suggested in the table, notice that none of these x's have a constant factor in front of them. If you do that and factor it out first so that you end up with this, then we can see that the corresponding constant in our substitution here is 1/9, or if you take the square of it, 1/3. So in this case, you would have actually, as the first step, would have seen the substitution x is equal to 1/3 sine theta. Now, of course, both methods actually yield the exact same substitution. You just have to divide this one by 3 throughout. So really just choose which way you prefer to think about it. I'm going to leave this last one for you to practice. I am simply going to say that you're going to utilize the exact same thing as in this integral before. So either think of this as 3x all squared, or figure out what you need to take out so that x is all by itself before you apply the substitution.